So this is exam one. D2L changed the way they calculate averages and stuff. So now the zeros of people who haven't taken it get factored into the average. Uh, so if you look at the average, it looks lower than it was. The average of the people who took it was about 85% or something like that. Um, Overall, it was pretty good. Two things that came up a lot. Uh, First is I don't know if this is what it's called, the integral rule. I'm going to call it that. So if you have the integral of x to the q dx, so that q doesn't have to be an integer. It can't be -1. Then this is equal to x to the q plus 1 over q plus 1. A lot of people did this wrong, and I actually didn't take off points for it because I think the reason people did it wrong originated in a solution that I had where I did it wrong, where I multiplied instead of divided, but you have to divide. So I just want to get that straight. Okay, so for example, if you have, like one way it came up was if you're taking the integral of v to the -1.2 power dv, that's equal to v to the -0.2 divided by -0.2, plus c, or in our cases, we're usually going to do definite integrals. All right, so don't multiply. So from now on, I'm going to take points off for that because we should know how to integrate. But I did it too, so we all need to be easy on ourselves, give ourselves a break on this. Okay, the second thing was one of these problems, number 3, was just purely about the main sign convention issue of this class. Well, thing number 2. So Q is positive if energy is added to your system by heat. Okay, so if heat increases the energy in your system, then Q is positive. Positive W means energy removed from the system by work. Or alternatively, you can also think of it as positive W means the system does work on the surroundings. Number 3 on the test was just entirely getting those straight, and think if you messed up on number 3 and uh, that fact gets you motivated enough to figure out what you did wrong and figure out how not to make that mistake in the future, then you should feel lucky you messed up number 3. You know what I mean? Because this is going to be a big deal on every test and every homework assignment from now until the end of the semester. Okay. There'll be a lot of points that you can gain or lose on that sign convention. Anybody have any specific homework, test questions you'd like to see me do, or any questions about any of them? Okay, well, why don't you look it over, and if you have questions, come talk to me in office hours or send me an email, and we can talk about it. Anybody have any homework questions? Yes. Mm-hmm. Well, if you're just talking about an isolated body and it's not surrounded by something else, then there's no difficulty in calculating the amount of heat that's radiated, but you have no way to calculate the amount of heat that's absorbed. And for the first law of thermodynamics, what you need is the net amount of heat, you know? And so it really doesn't do you any good to only get the amount of heat that's going out without knowing what's coming in. So for the first law of thermodynamics, we don't have any way to use radiation in the first law, unless the body is a small body surrounded by a bigger body. That's the only way we can do the first law. Mm-hmm. Um, that's a good question. Yeah, we're not going to do a lot of problems like this. We're only doing them right now. But yeah, that's a good question. I'm going to think about that and get back to you. Okay. Yeah. Um, any other questions or homework problems? Okay. Do you have that assignment with you? I don't have it in front of me. Okay. Oh, okay. So uh, this is from the heat set number 3. And it says the outer surface of a grill hood is 47 degrees Celsius. And the emissivity is 0.93. So is it better described by a matte black surface or a shiny white surface? Black closer to the black. The black is the 1 emissivity, the white is the 0. Um, the heat coefficient for convection is 10 watts per meter squared. And the surrounding air is 27 degrees Celsius. And we want to determine the net rate of heat transfer. So we want to calculate the net Q dot. So heat transfer is happening through radiation and convection, and we just have to do those separately and then combine them. So let's do the convection first. We know that Q dot is equal to 10 times, oh, you can't do it because you don't have an area, right? I think I remember seeing that, and I guess I didn't correct it. So let's give it an area. So the surface area is, let's say, 0.2 meters squared. Yeah. In watts per meter squared of surface area. Oh, yeah, you're right. Yep. Okay. But don't do this. Okay, so we got Q dot is equal to 10 times, is this how convection, remind me the equation. Is it, do I have an A in there? For, and then, yeah, okay. And then times the quantity, temperature of the surface. So that's 47 degrees Celsius minus the temperature of the fluid flowing over it. That's 27. So yeah, Q dot over A is equal to, that's 200. And then you have to think about, okay, and this is in watts per meter squared. Now you have to think about the sign. The grill hood is losing energy, right? Losing energy through convection to the surroundings. So this, think of this as heat lost by the grill hood. It's because this constant H has some crazy units. Watts per. Yeah, the units have to come out to be, I mean, Q dot is watts and area is meters squared, so it has to come out like that. But, and now radiation. So for radiation, Q dot is equal to the emissivity times the area times the temperature of the body to the fourth minus the temperature of the surroundings to the fourth. I might have switched the order of what I told you before, but we're going to think about the signs after we're done anyways. So let's just do it like this. So Q dot over A is equal to 0.93 sigma. Yep. Okay, so Q dot over A is the emissivity times the Boltzmann constant, 8.67 times 10 to the minus 8th, I think. What is it? 5.67. 5.67. 10 to the minus 8. And then we need these in Kelvin. So the temperature of the body in Kelvin, what's 273 plus 47? 320 minus 310, fourth, minus 310 to the fourth. And can someone calculate that? Yeah, yep. Can someone calculate that? What are we? Okay. 125.8. That's in units of watts per meter squared. And is there going to be net radiation lost from the grill hood or gained by the grill hood? And how do you know? Lost because the temperature of the grill hood is higher. And so the total Q dot over A is 325.8 watts per meter squared lost by the grill hood. Okay, so depending on what your system is, then if you're going to use that in the first law of thermodynamics, you have to think about whether your system is gaining heat or losing heat. And it could be either way depending on what your system is. For convection, it doesn't matter because if you had this as 320 and this is 300, it would still subtract. But since these are to the fourth power, it doesn't work. You wouldn't get the same thing. Yeah, you would have to, it has to be in, either you'd have to have all these units in Fahrenheit type stuff, or you'd have to change it to Celsius or Kelvin. But Celsius or Kelvin would both work. And the reason is so anytime you're talking about a difference in temperatures, Celsius and Kelvin are the same. But a difference of temperatures to the fourth power is different. Yep. Yeah. In both of those cases, yes, I think that's a good way to do it. I think that's a good way to do it with conduction too. Although when you start in different classes, when you start doing as a differential equation, you'll need that sign built into the math like that. Yes, that's right. So yeah, that's the kind of thing you have to think about when you put it into the first law. Yep. If the if the body temperature is greater than the surrounding temperature, then heat's lost. If the surrounding temperature is greater, then heat's gained. Any other homework questions? Yeah. That's one that there was a solution for. Okay, so this is differential form of the first law, number 3. So you have an electric generator coupled to a windmill. It produces an average electric power output of 15 kilowatts. So there's an electric power output of 15 kilowatts. So I'm going to write this as W dot. And is that W dot going to be, and I'm going to call it electric because I don't know if there's other power yet. Um, is that W dot going to be positive 15 kilowatts or negative 15 kilowatts? It's a power output. For the first law, work being done, this is, work being done by the system is positive. That's the sign convention. And so this is going to be positive 15. I'm going to call it 15 times 10 to the third watts. Power is used to charge a stored battery. And actually now that, okay, and then it starts talking about the battery. So we're going to have to think what the system is. It looks like our system probably is going to be the battery actually, which means that this work is coming into the system. And so that would be negative. That's energy coming into the battery through work. Heat transfer from the battery to the surroundings occurs at a constant rate of 1.8 kilowatts. So if the battery is losing energy to heat, is that Q dot positive or negative 1.8 kilowatts? If that's negative 1.8 times 10 to the third watts. For 8 hours of operation, determine the total amount of energy stored in the battery. Okay, so our equation says dE dt is equal to Q dot minus W dot. And so dE dt is equal to negative 1.8 times 10 to the third minus negative 15 times 10 to the third. And so that's positive 13.2 times 10 to the third watts. Watts are joules per second. So now we don't want to calculate the total rate at which energy is going into the battery. We want to figure out the total amount of energy over a time period. So how many seconds are there in 8 hours? So 8 hours is 8 times 3,600. What's that? Okay, 28,800 seconds. And so the way I like to think about this, so we have the dE dt is equal to 13.2 times 10 to the third watts. I'll just leave it like that. And you can solve this by separation of variables. So you can think of multiplying both sides by dt. So you have dE is equal to 13.2 times 10 to the third dt. And now you can integrate both sides. And you get that E is equal to the integral from time 0 to time 28,800 of 13.2 times 10 to the 3 dt, and that's 13.2 times 10 to the 3 times the quantity 28,880 minus 0. And what do you get for that? Something big. And now it's in joules. Any questions about that? Any other homework questions? When did we go till like 10 till 2? Okay, we got. So last time we started talking about full compressible substances. So last time we started this process. And one of the ways that we're going to get property values for simple compressible substances is from property tables. And the property tables that we're going to use come in 3 different forms. So there are 3 forms of table that relate properties to one another. The first are saturation tables. And there are going to be 2 separate ones. These are going to be, the first one is indexed by temperature. And it's going to have properties for a saturated liquid and properties for a saturated vapor. And then the second type is going to be indexed by pressure. And this is going to have the same information, properties for a saturated liquid and properties for a saturated vapor. Okay, these are the easy ones to use because they're indexed by a single property. You know, I said when I started talking about simple compressible substances that if you know 2 properties of a simple compressible substance, that's enough information to specify everything else about the state. If you're at a saturation state, you only need 1, and that makes sense if you think about like the boiling point or something. For a given pressure, if you know you're at the boiling point, then you already know the temperature. You know, the temperature for water needs to be 212 degrees Fahrenheit. You know, the fact that you're specifying a saturation state, you can think of that as like the other property that that lets you get all the other information. So these are easy to use. You just look down a list. If you're at a saturation state, though, most likely you're going to have some of your material in a vapor state and some in a liquid state. And so one thing that we're going to often talk about in saturation states is the quality. So how much of your saturated material is liquid and how much is vapor? Um, and we're going to use so it's called quality. It's going to be shown as a lowercase x, and it's defined as the mass of the material in the vapor state divided by the total mass of the material. So that's divided by the quantity mass in the liquid state plus mass in the vapor state. So if you have a material that's entirely vapor at a saturation state, what's the quality going to be? Right. So if it's all vapor, X is equal to 1. And if it's all liquid, what's X? 0. Yep. Okay, so notice if you're looking up stuff in the tables at the saturation temperature, at a saturation state, you're happy because these are the simpler ones to use. Because now we have to deal with states where you're not at the saturation state. It's all liquid away from the boiling temperature and pressure, or it's all superheated vapor. So the second type of table is called a compressed liquid table. And those are going to be separated into sections for a given pressure. Let's say separated into sections where the pressure is constant or the pressure is given, and then they're going to be indexed by temperature. The same idea is the table for superheated vapor. So it's going to be separated into sections where pressure is given. And then indexed by temperature. So let me pull these up and you can see what they look like. These tables are all available on D2L, all the ones you're going to need. All right, let's first look at a couple of saturation tables. So we're going to look at one that's indexed by temperature. Let's see, so saturated water temperature table. So this is, the material is water. We're at the saturation temperature, and it's indexed by temperature. Right, that's correct. Okay. I don't know what you can see here, but sort of read this stuff off. Maybe I can make it a little bigger. Okay, so properties of saturated water. You can see since now temperature and pressure are dependent on each other, you don't have to worry about the pressure, you can just read the temperature. And so say you have a temperature of 15 degrees Celsius. Well, you would have to have this pressure, in order for that to be the boiling point, you'd have to have a, incredibly low pressure for 15 degrees Celsius to make it boil. What do you expect the pressure to say in bar? So it goes on to the next page. Let's say we scroll down to 100 degrees Celsius. What is bar going to say? The pressure. One, exactly. Because the boiling temperature is 100 degrees Celsius at atmospheric pressure. By the way, do you know why it's really hard to cook when you're like for mountain climbers, like climbing the big mountains in the Himalayas? So it's hard enough to eat because you have no oxygen, you feel terrible or whatever. But it's also really hard to cook because you're at really high altitude, and so you're at a really low atmospheric pressure. And at a low atmospheric pressure, the boiling point is really low. And so if your water boils at 70 degrees, if you get above 70 degrees, your water disappears, but 70 degrees doesn't cook food very fast, And so you can't use dry heated stuff, what am I talking about? You can't use dried food, dehydrated food very well. Okay, so that's the pressure. And then it goes into specific volume. These are the other properties that you can read. Specific volume, internal energy, and that's also a specific internal energy. All of these are specific because you don't know how much you have of anything. Enthalpy and entropy, those will be important to us later. And in each one of these, we have two columns, okay? So if you're at 15 degrees Celsius and this low pressure that makes that the saturation state, then there are two kinds of things this material can be in two different phases. It can be a saturated liquid, in which case it has a specific volume of 1.0009 times 10 to the minus third, or it can be a saturated vapor, in which case it has a vastly bigger specific volume. As it goes from liquid to vapor, it's trying to expand a lot. For the specific volume, this says times 10 to the third, so it's a little confusing, but what that's saying is the value you see here is 1,000 times bigger than it really is. So, in other words, for water at 15 degrees and this pressure, the saturated vapor has a specific volume that's 77,000 times as big as the specific volume for the water, for the liquid. Internal energy, same thing. That's why all of these have two columns. So the one on the left is for the saturated liquid. The one on the right is the saturated vapor. And often you have to deal with the quality to figure out like what the combined specific volume is or whatever. Any questions on the format of that? That's the easy one to use because all you do is go down here, read the temperature off. There's also one of those for where it's indexed by pressure. I guess I won't pull that one up, but these are just flipped, So you just go down to the pressure you want, and then you read the temperature that it has to be if it's at its saturation state. Okay, now let's look at the compressed liquid table for water. Compressed liquid water table. All right, so now, since there are two independent variables, it's separated up into chunks that represent a single pressure. Okay, so this is for 25 bar, and now that we have that pressure set, it's indexed by temperature. So you have to go and find the one that has the pressure that you're dealing with, and then use the temperature index to find. And obviously the ranges are a lot smaller here because otherwise it would take up a lot more space. We have two independent variables. This time, so like specific volume, specific internal energy, specific enthalpy, specific entropy. They don't have two columns because this is for compressed liquid, so we're not dealing with vapor at all, you know. So there's only one phase that it can be in at this, if you're using this. Say that again. No, this is the end of, this is two separate sections. Oh, the 20 associates with that, but none of the other stuff. You're right, yes. And so all of these are like, they start at some temperature and go up to the saturation temperature, because once it gets to the saturation temperature, you switch to the other table. So yes, you're right. This is saying at 20 degrees Celsius, but at this new pressure. And then for the superheated vapor, it works just the same. So you're given a pressure. Once you find the pressure that you want, it's indexed by temperature. When you're dealing with the liquid tables, it went from some temperature up to the saturation temperature. Now these are vapors, so the starting is the saturation, and then from there it goes up. But you read them all off just the same. And since all of these are given as specific quantities, as intensive properties, if you want to go to like the actual volume or the actual internal energy, represent actual internal energy in joules or something, you're going to have to multiply by the mass of the material. Okay, but there's a problem with using the tables, sort of a difficulty. And that is, well, what if, like, how likely is it that your pressures are always going to be 0.06 bar or 0.35 bar or 0.7 bar or whatever, you know? We only have finite values here. Or how often is it that your temperatures are just going to be 80, 120, right? We need a way to approximate pressures in between the pressures that are given and to approximate temperatures in between the temperatures that are given. Yep. They're not linear, but that is how we're going to, that's how we're going to do it. We're going to do a linear approximation. So for us, it's easier for us to use, I mean, tables are easier to have access to than programs that do all this stuff. If you're working at a company or on a research project doing this, you're not going to be dealing with tables. You're going to have software that gives you those values. We're going to read it off of tables because it's convenient. But in order to, so if we wanted to deal with a superheated vapor at a pressure of 0.2 bar, say, and at a temperature of 165 degrees Celsius, um, using tables, we have to do a linear interpolation to come up with an estimate of what those values are going to be. And you might ask yourself, is it really worth learning linear interpolation if really when you're actually doing this stuff, you just type values into a computer and it spits it out? I think it is worth learning because this linear interpolation idea is going to be a big deal in, I don't know how many, I think probably none of you have taken numerical analysis at all yet, but all of you will. How to use computer approximations to solve problems that are hard to solve analytically. And this idea of linear interpolation is going to be, it's going to come up in a million different environments. And so we're just going to learn it here and you'll be happy later. But it's not, so I'm going to do it now. It's not really for the thermodynamics that we're going to do it. We're just going to do it because it's going to be a key idea going forward. Okay, so linear interpolation. Yeah. So the idea is if you know function values, let's say if you only know function values at a finite number of points, this is a way to approximate function values between the points. And you can do it with any number of independent variables. For us, all that matters are one or two independent variables. So we'll use it with one independent variable and with two independent variables. Okay, so what's the type of table where we're going to do a linear interpolation with one independent variable? There's only one type of table that we'll deal with where that's useful. That's for the saturation tables, because those are the ones where a single property is all you need as an index. So all we ever have to approximate for the saturation tables are like, it'll have a row for 80 degrees Celsius and a row for 90 degrees Celsius. And if we want 84, we'll interpolate with one independent variable, the temperature. For the other two types of tables, we're going to need to interpolate for the pressure and also for the temperature. Okay, so for those, we'll need to interpolate for two independent variables. Okay, so let's start with functions of one independent variable. And the idea is this. So this is the independent variable. I'll call it X here, but it'll be temperature or pressure when we use it. and this is the dependent variable. This is the function value, and that's going to be, so I'll call that, well, I'll call that f of x. But when we do this interpolation, that'll be one of those other properties that we're going to be calculating as a function of temperature or pressure. And so let's say this function looks like that. Now, if we know a mathematical functional relationship between those, then we're done. But what if we don't know a mathematical functional relationship? What if we only know a value here? Let's call that x1, and a value here, we'll call that x2. And we know that the height then here for this one is f of x1. And the height here is f of x2. And just to be, I'm going to call this f1, but that's what it means. f1 is the function value at x1. f2 is the function value at x2. Let's say that we want to approximate this function at some value x. So how do we approximate f of x given f1 and f2? The idea is that we assume that between those 2 points, the function is linear. And then our approximation just uses where the, assuming that that's a linear function, we're going to treat this as our sort of temporary function representing this x. We're going to figure out what f of x is for that line. And I think that picture sort of explains why this is a better approximation than just using either of the two endpoints. It's not perfect because this isn't going to be a linear function, but the closer these two are together, the better that approximation is. And so the formula we're going to use is that our f of x approximation is going to be approximately equal to f1 plus the quantity f2 minus f1 divided by the quantity x2 minus x1 times delta x. And delta x is just x minus. Yes.
Why do you do the F1 plus? Oh, I got to count for the first part.
Yeah. Okay, so let's do an example, and then I'll stop for today. So let's use linear interpolation to approximate f of x equals x squared at an x value of 2, given that f of 1.5 is 2.25 and f of 2.5 is 6.25. Okay, so we know function values at an x value of 1.5 and an x value of 2.5. We're going to use linear interpolation to approximate the f value at x equals 2. Any questions about the problem? Okay, so f at 2 is about equal to f at that first point, so 2.25 plus, in the numerator, we have the quantity f2 minus f1, so that's 6.25 minus 2.25 divided by x2, the quantity x2 minus x1, so that's 2.5 minus 1.5. Delta x is your x value minus x1, so that's going to be 0.5. And I got so excited I used values that weren't in my notes, so can someone calculate that? What? 2.1? 2.5. 4.25. Okay, so those two, x1 and x2 are pretty far apart. But it gives you something in the ballpark. If we moved those, if we changed those to 1.9 and 2.1, we'd get a value that was a lot closer. The true value, what's the true value? 4, yeah. So it's pretty close to 4. Any other questions about that? Okay. Well, I think I have some problems where you can sort of get used to that. I hope I do. So, and on D2L, let's do the quiz.